This is a very standard NPN type transistor and it consists of three layers. The emitter, which is heavily doped, the collector, which is moderately doped, and the base, which is very thin and very lightly doped. So there is a depletion layer which forms here as we have studied in diodes, and it is highly exaggerated here. And there is an electric field around this depletion layer. In a standard NPN transistor, the strength of this electric field is about 0.6 volts. Now if we connect a battery across the NPN transistor, we see that nothing really happens. One may argue that this emitter is in a forward bias position and it should push the electrons and cause the flow of current. But we notice that the base here is not forward biased and therefore it is not helping in breaking this electric field here. On the other hand, this reverse bias is actually pulling the electrons and strengthening the electric field here and causing the depletion layer to widen. Now when the emitter is put in a forward bias position, things change. The electrons in the emitter push through the depletion layer and start to flow in the emitter base circuit. So notice that this is the flow of electrons and the direction of current flow will be put in the opposite direction. The base is lightly doped and therefore the current in the base emitter circuit is still small. The electrons from the emitter which have crossed the depletion layer and have reached the base get attracted to this positive electric field and break through this depletion layer. And this suddenly causes a large flow of current in the collector emitter circuit. This amplification of current is known as beta, and this could have values like 20 or 200, and it's a property of the material, the NPN transistor. By Kirchhoff's law, current in the emitter is given as a sum of IB plus IC. The electrical circuit diagrams with the transistors could look very different. So here we try and map what we have seen to a circuit diagram. So here we have basically rotated this particular transistor. So we have the collector here, the base, and then the emitter here. And this is the forward bias and this is the reverse bias. In electrical circuits, which we will see, we will also find input resistance and some output resistance along with the reverse bias and the forward bias. We will first focus on the input characteristics, and that is the change in base current versus change in the base emitter voltage. So we know that the depletion layer across this PN junction is about 0.6 volts. So what we notice is that when we increase the base emitter voltage from 0 to about 0.6 volts, there is no current flowing because the depletion layer is still there. But after this 0.6 volts is crossed, we see that the current starts to flow in the base emitter circuit. We also notice that there is a small variation with respect to the collector emitter voltage. So when the collector emitter voltage is increased, the growth of the current is little slower in the base emitter circuit, and that is because more electrons get pulled in the collector circuit when this reverse bias is increased. For output characteristics, we will look at current in the collector circuit versus the reverse bias. And here we see that this graph can be broadly divided into three regions. There is this active region. This is the region which is commonly used for amplification, and therefore it is called the active region. There is a cutoff region and there is a saturation region, and we will discuss these three regions shortly. So what we notice in the active region is that the emitter is in a forward bias situation and the collector is in a reverse bias situation, which is the common expectation. And here we see large amplification of the base current. So for 0.1 milliampere, we see almost 5 milliampere in the collector circuit. So this region corresponds to this particular region in the input circuit. So here the base current has started flowing, and this is what is getting amplified and seen as the collector current. So in the cutoff region, both the emitter and collector are in reverse bias, and the collector, because it has about say 15 volts, it is understandable that it is in reverse bias. The question is, how come emitter is in reverse bias? It should be in forward bias. So notice here that IB is equal to 0, the base current is 0, which means that this circuit is operating in this region of the graph, and here the base voltage is less than 0.7 volts, and therefore it is said to be in reverse bias. So in saturation region, both the emitter and collector are in forward bias, and we see that the base current is more than 0 and it is operating in this region, and therefore the emitter is forward biased. The question is, how come the collector is forward biased? Now if we see here, the collector emitter voltage is very close to 0, and if we assume that it is less than 0.7 volts, which is the electric field around the depletion region, we can consider that the collector emitter circuit is nearly in a forward bias situation.